Hi, my name is Shahnawaz. In last lecture, we did subcategories and full subcategories. So let us quickly recall what do we mean by a subcategory. So suppose we have a category A and a category B. Then we say A is a subcategory of B. If if A satisfies the following conditions. The condition first is that the object class of A, it has to be this is contained in the object class of B. Second is that if we pick any two objects, say A and A prime in category A, then if we look at the set of morphisms from object A to A prime in category A, so it is contained in the set of morphisms from the same objects A and A prime, but in category B. Finally, if we look at the object A in category A, then the identity morphism on object A in category A, it has to be same as the identity morphism on the object A in category B. And finally, if we look at the composition law in category A, that has to be the restriction of composition law in category B to the morphisms of A. So if these four conditions are satisfied by the category A, then we say A is a subcategory of B. In last lecture, we did some examples where we saw that this sometimes this inclusion is replaced by the equality, and those subcategories are called full subcategories. So a full subcategory is a category where if we pick any two objects in A, then the set of morphisms between these objects in category A is same as a set of morphisms between the objects between these objects but in category B. Those subcategories are said to be full subcategories. Now uh, we have a remark to make here. So if we consider a subcategory in B, then there is always associated an inclusion functor. So for every subcategory, say A of a category, say B, there is always uh, associated and inclusion functor. And we let us note that functor by I. So this inclusion functor is from category A to category B, and this behaves like the identity. So this is defined by. So if we have a morphism between objects A and A prime in category A, so this functor takes these two objects to the morphism F in the category. So this is so A goes to, so this is A prime here. So A is carried to A prime is carried to A prime, and F is carried to F. So these A and A primes, they are actually the objects in A, and F is a morphism in A. So for all A and A prime in the object class of A, and for all morphisms F in A. So Not only that, such an inclusion, I mean, such a functor is an embedding. So, moreover, such a functor is, first of all, it is an embedding. To call that an embedding is a functor uh, which is injective on morphisms. And second is that, so this is a full functor if and only if A is a full subcategory. Recall a full functor is a functor which, when restricted to home status, is surjective. So this is a full functor. I mean this inclusion. This is a full functor if and only if A is a full subcategory of B. I think it is better to recall what do we mean by a functor. I mean, when we say a functor is embedding, or when we say a functor is full or faithful. So recall, so we have a category, say A, then we often denote it is object class by OB of A, and the set of all morphisms in A, we usually denote that by MOR of A. This stands for morphisms in a morphism class in A. And if we pick two objects, say A and A prime, in the object class, then the morphisms, set of morphisms, I mean the set of arrows from A to A prime, is denoted by home A prime. So these are the morphisms in category A from object A to A prime. So with these notations, one can note here that this morphism class is actually the set of all these home sets. So this is the union of all home A prime. I mean the in the category A, where these A and A prime, they are objects in the category A. Now, what a functor does, so if we have a functor, say from category A to category B, so this functor is actually a map between the object class of A and object class of B, and similarly it is also a mapping between morphism class of A and a morphism class of B. So if this functor is injective on morphism morphism classes, then we say F is embedding. I mean, if we have two morphisms, say F and F prime, they are in uh, they are two morphisms in category A. So if F and F prime are not equal, then F of F, which is a morphism of so if this is I mean if for all morphisms F and F prime in A, where F and F prime are not equal, so if F of F is not equal to F of F prime, then we say this F is embedding. I mean, we say this is embedding, where F of F and F of F prime, they are the morphisms in the category B. I mean, if this functor F is injective on this class, so we say F is an embedding. Now, when do we say F is a faithful functor? So again, we have a category A and a category B. So we say a functor between these two categories is a faithful category if we restrict to this functor to the home set. So if we take two objects here, say A and A prime, they are the two objects in category A. So this functor takes this class to home of f of a. Now f of a is an object in the category B, and f of a prime is also an object in the category B. So this uh, morphism set is in category B. Now if this functor is injective, we say f is faithful. Now one may be wondering, then what is the difference between a faithful and an embedding functor? So the conclusion here is that every embedding is a faithful functor, but not conversely. I mean, if f is a faithful functor, that need not be an embedding, but embedding is always faithful, because uh, this embedding is injective on the set of all morphisms, i.e. the morphism class of category A. However, so this is if f is injective 1 1, this will imply f is embedding. However, if we restrict this morphism to the morphism set between two objects, so this is the restriction to some particular class of arrows. So if this is injective 1 1, this would imply f is faithful. Now let us give an example where uh, we can see a faithful functor need not be an embedding. So let us consider a category A and a category B. Suppose category A has only two objects. Say it has an object A and an object A prime, and a category B has only one object, say B. So if we look at the object class of category A, it is just two objects, A and A prime. And if we look at the object class of category B, it is just the single object, that is the object B. Now if f is a functor between these two categories, then this f is also a map between these two classes. So it naturally maps the object A and A prime to the same object B. Now here if we look at so there is no morphism between A and A prime. However, we know every object has an identity morphism over it. I mean, we have the identity map over A. I mean, a map from A to A. Similarly, a map from A prime to A prime, which we denote by 1 sub A prime. Similarly, here we have the identity map 1 sub B. So if we look at the morphism class of category A, it is just two maps. I mean the map 1 sub A and 1 sub A prime. And if we look at the morphism class of B, it is 1 sub B. Again, this functor is a map between these two classes as well. So it takes the morphism 1 sub A and 1 sub A prime, and it maps these two morphisms to the same morphism, which is 1 sub B. So one should note here, if we look at the home set A to A prime, there is no morphism. So this is empty. Similarly, home A prime to A, this is also empty. I mean, there is no map between these two objects. However, if we look at the home set A to A, then it is just the identity 1 sub A. Similarly, if we look at home set, I mean the morphism set from A to A prime to A prime, it is 1 sub A prime. Now let us restrict this functor to this home set. So then we have a map from home A to A to home B, sorry, this is A here, B to B. So it this set has one element which is 1 sub A, and this set has one element which is 1 sub B. So this functor takes naturally this morphism to this morphism. So I mean, when we restrict this functor to this home set, it turns out to be injective. So the restriction of f over this home set is injective. But for f to be faithful, it has to be injective when restricted to any home set. So if we restrict this functor to this home set, it also turns out to be injective, because in that case home a prime contains just one element, which is 1 sub a prime, and similarly home b is a prime to a prime. So this is 1 sub b. So naturally it takes this morphism to this morphism. So one can note here that every embedding is a faithful, I mean every embedding is faithful but not conversely. So this is the example where one can see the difference. Now we I mean um either it is an embedding or faithful functor, it need not be injective on the object class. Because if we look at the category of groups and we look at the category of sets and we just consider f to be the forgetful functor. Now, what this forgetful functor does, it takes an object here, which is a structured set. So it just forgets the structure and it maps it to the underlying set. So if we have two groups here, suppose we have two objects g1 and g2 here. So suppose they are non-isomorphic. So g1 and g2, they are non-isomorphic. So one can note here this functor is faithful because it takes group homomorphisms and it maps the group homomorphisms to just functions between these sets. So here g1 and g2, they are non-isomorphic group. Suppose their underlying set is same. Now, what this forgetful functor does, it identifies, I mean, non-isomorphic groups, because if we look at G1 and G2, they are as groups, they are distinct objects because they are non-isomorphic. But as sets, since we are saying that G1 and G2 have same underlying set. So this functor takes these two distinct objects to one object, because what this functor does, it forgets their group structure. So when we drop the group structure of G1 and G2, we are left with a set. Similarly, if we look at this functor, if we restrict this functor to any home set, it turns out to be uh, injective. So this forgetful functor is faithful. I mean, it is injective when restricted to home sets. However, this functor is not injective when restricted to the object class, because we have seen here, if we consider two non-isomorphic groups, they are mapped to the same set. So that means a faithful functor need not be injective on the object class. Now we want to prove a proposition, I mean a result, which states that the inclusion of subcategories up to isomorphism are precisely in the embedding functors. So the statement of the result is like this. So we have a proposition. So we say a functor, let us call this functor f, from a category A to category B, is a full embedding even only if there exists there exists a full subcategory. Subcategory say D of B with inclusion. So we know when we have a subcategory, then we have the associated inclusion. So here the inclusion is with inclusion, say I from D to B. So this I is actually a functor and an isomorphism. Say G from category A to D with, so with F is I composite G. Hmm. Now let us prove this. So what we have to prove actually? So we have a category A and a category B. So we are saying that this. So one should note here we just. I mean, if this result states that a functor f is a full embedding if and only if it's a full subcategory. So if we drop full here, so we have to drop full here. So it is full embedding if it is full subcategory. Otherwise, it is embedding if and only if it is a subcategory. So let us prove this. So first we are going to assume that f is a full embedding. Then we have to prove that there is an inclusion I from D to B, where G from A to D is an isomorphism with f from I with f um, same as I composite G. So one should note here we say a functor from categories A to B is an isomorphism if there is another functor say G from B to A, such that G composite F is the identity functor on category A and F composite G is the identity functor on category B. So in some sense it says that uh, a functor, I mean a functor is isomorphism if it is full faithful on I mean it is injective as well as surjective on both sets. I mean the morphism class as well as the object class. Now let us prove this. So let us first assume that f is a full embedding. So suppose f is, so actually this statement I mean there are two statements in this result. One statement is without full here, so if we drop full here then we get one statement, and other statement is if we include full here, so it is full embedding if and only full subcategory. Otherwise it is embedding if and only if um, we have a subcategory here. So suppose f from suppose f from category A to category B is a full embedding. So it's a full embedding. Now let us, so by embedding we mean this F is injective on the morphism class. Now let us consider D to be the image of F within B. So let D be the image of F uh, within B. So in last lecture, we saw that the image of a functor need not be a subcategory. But when f is an embedding, then the image is always a subcategory. So that means this D is a subcategory in B. Now, when D is a subcategory in B, we have the associated inclusion functor. So since this F is uh, a full embedding, that means D is a subcategory of B. So if that is the case, we have an inclusion from D to B. Hence, there is an inclusion, say I from D to B. So that means we can embed D into B. Of course, D is embedded into B because this D is actually the image of F, image of A under F. So one should note here that the category D and category A are isomorphic because this F is full as well as faithful, because F takes this A into B and F maps A to D. Now F from A to D, F is given to be embedding. Now restricting the codomain to the category D, it turns out to be full as well. So that means F is an isomorphism. In other words, there is a map G from D to uh, A, which is isomorph. I mean, there's a map G from D to A such that, uh, or in other words, we can call this map G because F is a map from category A to B. And if we restrict to B to D, then we replace this F by G. So in that case, G is again a functor which is embedding as well as full. Now by embedding, it is also by embedding it means it's faithful. So that means this G from A to D is an isomorphism. So note that A and D are isomorphic, and let say G from uh, say A to D be the isomorphism. So this is what we have to prove here. Now we have to prove this F is actually I composite G. So now with G being the isomorphism, one can note that the diagram, if we look at the diagram, say D is here and we have category A here, category B here, and from A to D we have the isomorphism G, which is a functor, and from D to B we have the inclusion I. So from A to B we have the functor F, but this turns out to be the map I composite G. So this is the map, but so this is I composite G as well as this is the functor F. So hence the following diagram commutes. That is, this F is same as I composite G. Now the converse follows from the fact that uh, I mean, embeddings are closed under this operation. I mean, so the converse, I mean, the other directions, the other direction follows from the fact that embeddings are closed under composition. Suppose we have an embedding, say, suppose F from category A to category B, and an embedding G from category B to C. And then if we look at the composition G composite F, this is also an embedding. So using this fact, one can see over here, this is an embedding because G is an isomorphism, hence an embedding. I is also given to be inclusion and hence an embedding. Now, if we compose these two maps, we are so in the other direction we have to assume that F is same as I composite G. Now I is embedding, G is embedding. It turns out to be F is embedding, and hence F from A to B will turn out to be an embedding. So this is this straightforward. Now we want to define the fully embeddable categories. So we have this definition here. So a category, say A is said to be fully embeddable. So it is said to be fully embeddable into a category B, provided that there is a full embedding. Provided that there exists a full embedding of category A into B. So if we can embed A into B, I mean fully. So if there is a functor F from category A to B, which is an embedding as well as full, we say this A is fully embeddable into category B, or we can write here, or equivalently, uh, provided A is isomorphic to a full subcategory of B. So if A is isomorphic to a full subcategory of B, we can say A is fully embeddable into the category B. So one should make a remark here that the full subcategories are determined by their object class. So they are often regarded as the properties of objects. So a fully embeddable subcategory is determined by the properties of its object class. So we should make a remark here. So since full subcategories are determined by their object classes, So, with this reason, they are often regarded as properties of objects. They are often regarded as properties of objects.